Hey everybody! In this video, 2.4 GHz transceivers based on NRF24 chip are tested. To perform the test, we will assemble two test modules. We use two network controllers that have various network tests in their firmware. We will use GPS to measure the distance between the transceivers. Assemble the modules as shown in the user manual. Connect the GPS keyboard and display to the network controller. Use the AT command to configure the controller. This concludes the preparation of the modules for the test. Now let's check the test modules in operation. Switching on the power. The display shows the main parameters of the network nodes. See the configuration of the network nodes. Here we see the network address, network node address, receiver node address, and our channel number 85. Start scanning channels. We see that all channels are free. The operating channel number is displayed 85. Trying to run a transceiver test. No luck. The reason is different bitrate. The module on the left has 250 kilobits per second. The module on the right has 2 megabits per second. Set the same bitrate 250 kilobits per second. Let's run the test. The left module is the transmitter and the right module is the receiver. The display shows the counter value, the number of transmission errors, and the distance between transceivers. Test of packet transmission with bitrate 250 kilobits per second passed. Set the bitrate to 1 megabit per second. Let's run the test. Packet transmission test with 1 megabit per second bitrate passed. Set bitrate to 2 megabits per second. Let's run the test. Two megabits per second packet transmission test passed. Let's check the operation of the modules with the network monitor. Let's run a channel scan. Let's make sure that our working channel is free. Let's run the test. Test passed. Checking the error counter. Let's run the test. The values of the incremental counters are synchronized, so the error counter is 0. Reset the value of the incremental counter on the left module. The test is resumed and the error counter is no longer 0. Let's reset the incremental counter once again. After resuming the test, the error counter value increased. Let's go over it again. The error counter is working correctly. Let's make sure that the module channel scanner works correctly. Let's start channel scanning and see that the channels at the beginning of the band are busy. The same busy channels are displayed on the dedicated device. On the left are the router's Wi-Fi channels. On the right is our working channel with a number 85. This implies that the module channel scanner is working correctly and can be trusted. For an objective evaluation of the performance of different transceivers in the test, the same antenna should be used. Unfortunately, not all antennas have the same characteristics. Therefore, there is a need to check the antenna with a special device. We are interested in the frequency interval within which the standing wave coefficient, or VSWR, has the lowest value. Our task is to select two antennas with VSWR close to unity in the middle of the operating range. Connect the antennas to the device in turn and see the VSWR value on the fourth division of the scale. First antenna, great antenna for the end of the range. Second antenna, mediocre antenna for the beginning of the range. Third antenna, it's a great antenna for the end of the range. Fourth antenna, excellent mid-range antenna. Fifth antenna, great antenna for the end of the range. Antenna 6, a great antenna for the beginning of the range. Antenna 7, a great antenna for the end of the range. Eighth antenna, it's a great antenna for the beginning of the range. Antenna 9, a great antenna for the beginning of the range. 10th antenna, a defective antenna. It happens. The answer to why the device does not work. 11th antenna, average antenna for the beginning of the range. 12th antenna, great antenna for the test. 13th antenna, great antenna for the test. These two antennas have been tested before, so they have the tags on them. Let's look at the antenna design and check the effects of the antenna body on the antenna characteristics. Remove the antenna housing and connect the antenna to the device. We see that the antenna resonance has shifted towards the end of the range, which is quite expected. Return the case and see the result. Everything's back to normal. Checking the accuracy of the GPS. Set the GPS data update rate to 5 times per second. GPS accuracy 2 meters. Let's start checking. 0 meters is fine. 1 meter is fine. 2 meters is great. 3 meters does not exceed the error value. 4 meters is fine. 5 meters is fine. Let's go to testing the transceivers in open terrain. Test conditions. The transmitter and receiver antennas are located at a height of 1.7 meters. The transmitter is standing still. The receiver is moving away. The information on the display is captured on the camera. First test. Bitrate 250 kilobits per second. Let's see. 50 meters. 100 meters. 200 meters. 300 meters. 400 meters. 470 meters. We can see that the distance is changed, but the counter value is not. Why? The counter value will only increase if a notification is received for the previous packet. GPS data is sent as is. Bitrate 1 megabit per second. Let's see. 50 meters. 100 meters. 200 meters. 300 meters. 345 meters. Bitrate 2 megabits per second. Let's see. 50 meters. 100 meters. 200 meters. 270 meters. Second test. Bitrate 250 kilobits per second. Let's see. 100 meters. 500 meters. 1,000 meters. That's the distance claimed by the manufacturer. 1,050 meters. 2,000 meters. Single packets come in at a distance of 2,200 meters. Bitrate 1 megabit per second. Let's see. 100 meters. 500 meters. 1,000 meters. 1,050 meters. 2,000 meters. 2,080 meters. Bitrate 2 megabits per second. Let's see. 100 meters. 500 meters. 1,000 meters. 1,050 meters. Third test. Let's see. The transceiver is similar to the previous one, but a different type of antenna. 100 meters. 500 meters. 1,000 meters. That's the distance claimed by the manufacturer. 1,050 meters. 2,000 meters. 2,130 meters. Fourth test. Bitrate 250 kilobits per second. Let's see. 100 meters. 500 meters. 1,000 meters. 1,050 meters. 2,000 meters. Single packets come in at a distance of 2,200 meters. Bitrate 1 megabit per second. Let's see. 100 meters. 500 meters. 1,000 meters. 1,050 meters. 2,000 meters. 2,200 meters. Bitrate 2 megabits per second. Let's see. 100 meters. 500 meters. 1,000 meters. 1,050 meters. 2,000 meters. 2,380 meters. For experimental purposes, let's check the packet transmission distance in a deciduous forest. We'll be testing 2 transceivers. First transceiver, let's see. 50 meters. 100 meters. 150 meters. 200 meters. Second transceiver, let's see. 50 meters. 100 meters. 150 meters. 200 meters. 250 meters. 300 meters. Let's test transceivers with a transmitting antenna height of 3 meters and a bit rate of 250 kilobits per second. First test. Let's see. 1,000 meters. 2,000 meters. 3,000 meters. Unexpected obstacle. Waiting. 4,000 meters. 5,000 meters. 6,000 meters. 6,600 meters. 6,440 meters. Two-way communication is stable. Second test. Let's see. 1,000 meters. 2,000 meters. 3,000 meters. 4,000 meters. 5,280 meters. Third test, let's see. 1,000 meters, 2,000 meters, no direct line of sight, 3,000 meters, 4,000 meters, 5,000 meters, 6,000 meters. The Fresnel zone allows the reception of individual packages on top of trees. 7,000 meters. Areas of line of sight appearing. 8,000 meters. There's a two-way packet exchange. 10,000 meters. No line of sight between nodes. 10,500 meters. 10,400 meters. Two-way communication is stable. 10,270 meters. Direct visibility between the nodes has been established. Two-way communication works perfectly. Conclusions. The test results show that all transceivers meet their specifications. There were no data errors during the testing process. Thank you for watching. Good luck, everyone.